So let's continue. Now we'll consider transformations in complex plane. In the complex plane, we will suggest that transformations or maps are functions from complex plane onto the complex plane, and this transformation is one-to-one. So it is one-to-one and onto transformations that we are going to consider. Onto and one-to-one. And as you will see pretty soon, it's not possible to consider these transformations that we will deal with as onto and one-to-one in the complex plane, but we will improve our complex plane a little bit. We will make the so-called extended complex plane, and then it will be just fine. So, what kind of transformations we will consider? We will consider specific, what we can call geometrical transformations and compositions of these transformations, because various what we call groups of transformations, we have already met the notion of a group in elementary geometry. We had dealt with a group of isometries. Groups of transformations generate geometries in the complex plane, and that's what we are going to consider in this class. But first, let's just consider specific transformations and some of their properties. So, what kind of transformation do we consider? Translations. Translations in elementary geometry, we call them also parallel translations. In elementary geometry, we use them for constructions. Yes, we call them parallel translations. What translations do? They translate every point in the complex plane, or every vector of the complex plane, by a certain vector. So, for instance, if we have a complex plane here, this is the real part Z, this is imaginary part Z as usual, we can translate all the vectors, all the points of the plane, by a certain vector. Suppose by this vector. But this vector that we will call it, for instance, gamma equal A plus IB. So the origin will be translated at this point, gamma with the coordinates A and B. So this point of the graph. And any other point will be translated by the same. So, for instance, this point translated, I will just take a vector of the same length and the same direction, something like this. Property of the same. Yes? So, if this is point Z, this will be translation applied to Z. If this is point, let's say this point is xi, it's a Greek letter xi, it's very easy to write. You write a little loop and then whatever, the long tail. It will be translated into this point, which will be t of xi. And what exactly is going to be? It will be xi plus A plus IB. And so a similar thing will happen to every point in the plane. This point A will be translated into this point, t of a. Certainly, since it is an isometry, it possesses all the properties of isometries. In particular, we will be interested in one property, which is called the conformality. Conformality or preservation of angles. So, angles do not change under transformation t. Then t is called conformal. Or we say it possesses the property of conformality of angles. And certainly the translations possess this property. The next property, rotations. Rotations. So what are rotations? When you rotate the whole plane about a certain point at a certain angle. For instance, that's your complex plane. This is part Z. This is imaginary Z. So suppose you rotate the whole plane about the origin through certain angle theta. So every point will move into a point standing at the same distance from the origin, but obtained through rotating the vector connecting the origin with this point about a certain angle. So suppose this is point R, some real number, yes? Then as a result of rotation, the angle theta, suppose this is angle theta, it will transform into point R multiplied by e to the power I theta. You know that when we multiply two complex numbers, their moduli are multiplied and their arguments are being added to each other. Yeah? So for instance, if we have complex number z1 multiplied by z2, so their product will be r1 e to the power I theta 1, r2 e to the power I theta 2, or it will be r1 r2, the modulus of the product, e to the power I theta 1 plus theta 2. So rotation through theta is obtained by, I will continue writing here, multiplying the numbers that we are considering, or numbers if we are talking about the whole plane, by what factor? By e to the power I theta. This factor, right? This will not change the modulus of the complex number, but it will rotate the numbers through angle theta. So for instance, if we have some number at distance rho on the imaginary axis, the distance is rho, then rotating through angle theta, we will obtain this number, right? And this number will be the original number, this one, I rho multiplied by e to the power I theta. What about some other number? What about What about this number? The same story with this number. Just rotate this vector connecting the number with the origins through angle theta, and you will obtain this number. So if this is z e to the power I theta. I have to erase the first part, and then I can make a better picture. So we are considering now rotations. Rotation about the origin. Z is transformed into number W, let's denote the W, equal rotation applied to Z. I can write T theta Z, rotations to angle theta. Rotation through angle theta about the origin. T of Z will be e to the power I theta multiplied by Z. It's not really new for you because you know how we multiply complex numbers, right? Translation, each complex number is a vector, yes? When we translate the whole plane by a certain vector, we just add this vector to every position vector of the plane, every point in the plane. If you rotate, you multiply each number by e to the power I theta, and you will receive the image of this number. Yes? What about the rotations around not the origin, but some other point? Rotation about some point z0 through angle theta. What shall we do in cases like this? I think it's pretty easy. We will just say the following. So suppose we have this complex plane, origin is somewhere here, and there is this point z0, and we want certain point z, this point for instance z, to be obtained as a result of rotation of the whole plane around z0, not the origin anymore, right? So we will say, what is this vector? This vector is z minus z0, right? Z minus z0 must be rotated through angle theta. And as a result, we obtain this image W, right? This image W, I will say W is the image of Z. So what can we say about W? It is the vector Z minus Z0 is being rotated through angle theta. So I can say W minus Z0, this vector, W minus Z0. This, you can actually draw arrows if it helps you. You know vectors. W minus Z0 is obtained by rotating through angle theta of vector Z minus Z0. That's all we have to do. And this is, I will say, formula number 1. This is much more convenient than the approach offered in your textbook when solving certain problems. Right? We don't really care about this, that origin is not at the point z0, because we can consider rotation about z0 right away we'll just consider the differences of vectors instead of vectors, yes? Instead of considering the vectors themselves, vector Z, vector W, it would be really complicated to consider these vectors, but instead we consider just their differences with the point Z0 about which we rotate the plane. For instance, if I look at some problems in your textbook, it's not really a good advice. It gives you example and tells you how to solve, for instance, the first problem. Problem number 5a. Find the formula for rotating the plane by 45 degrees about the point I. 5a. Rotation of the complex plane through 45 degrees about, I will denote my notation, Z0 equals to I, about this point. So it is problem number 5a. In some textbooks of linear algebra, they like saying rotated counterclockwise, rotated clockwise. If it says rotated through 45 degrees, it means counterclockwise. If they wanted to say rotated through 45 degrees clockwise, they would say rotated through negative 45 degrees. Right? So, what do we do in cases like this? We just say there is this point, again, there is this point Z0, I don't even want to draw the origin or anything else. And there is point Z, suppose it is somewhere here. And we must rotate it through 45 degrees. So, as a result of rotation through 45 degrees, this will be 45 degrees, we obtain new point W. It's always short of look pretty clear that it must be a vector of the same length. Right? This is the point W right here. About Z0 equals to I. So what do we see here? You don't have to remember this formula, it's just common sense. This vector is obtained from this vector by rotating through 45 degrees. So W minus Z0 will be e to the power I theta for any angle. Z minus Z0. In our particular case, W is the image, yes? W standard notation for the image of Z. So W minus I equals e to the power I pi over 4 Z minus I. So I will go from here. So W equals, I will send I to the right hand side, I plus e to the power I pi over 4 is cosine pi over 4 plus I sine pi over 4. And 1 over root 2 plus I 1 over root 2. And multiplied by Z minus I. That's it. That's a formula. We can maybe simplify it, work on it a little bit more and obtain the same expressions I have in the textbook after very long and confusing explanation. Don't even read it. So I will say W equals, I will bring to common denominator and multiply I by root of 2, I root of 2 plus 1 plus I multiplied by Z minus I multiplied by 1 plus I and divided by root of 2. So what's going to be if I didn't make mistakes altogether? I multiplied by root of 2 minus 1 and plus 1. I root of 2 minus 1 plus 1 plus 1 plus I z divided by root of 2. I think we can leave this form. It will be fine. Any questions about this? I think that's all the form, all the things you have to understand. You have to always draw a little diagram, your point around which you rotate, old point and the new point. You don't even need anything else on this diagram. That's the formula for rotation. The next type of transformation is a stretch or shrink transformation or dilatation. Sometimes they call it dilation, but the preferred word is homotety. It's a homotety. What homotety does? Homotety creates a similar figure from a certain point called the center of homotety. So if you perform the homotety about the origin, homotety with the center of similarity or center of homotety at O, will look like this. You have a certain point Z, you can see such a vector, and you multiply each point of the plane by a certain positive real number. For instance, if I multiply number by some coefficient greater than 1, that will be your W equal K Z. Right? W equal Kz, where K is a real number and K is positive. That's a homotety, right? Homotety translates figures into similar figures. You know what happens? Similar and similarly situated figures. What if you perform a homotety, for instance, of some triangle? Suppose this is the triangle to which you apply homotety. You know how you apply it. We solve these many problems in elementary geometry using this homotety thing. That will be the image of this triangle. Yes? This will be the image. You will obtain a similar triangle, and each angle is preserved. So, for instance, if this angle alpha, this is still alpha. If this is angle beta, this will be angle beta, and so on. So, the same as rotation. Rotation is isometry, so of course it possesses conformality. Yes, the homotety transformation are conformal. They preserve angles. Angle alpha is transformed into congruent to it angle alpha. Homotheties are conformal, they preserve angles. What if you want to perform a homotety with the center not at the origin but at some other point? Just the same story as with rotations. A homotety with the center at Z0 and the ratio or similarity ratio, usually we just say the ratio, K. How will we perform it? So this is point Z0, which is the center of our homotety, right? And this is some other point Z. So what will we do with this vector? This vector must be stretched or shrunk, because it may be that coefficient k is less than 1, yes, in the same direction. We get a linear vector. So this is vector w equal t of z. So what is, I will make this vector from z0 to z a little bit more visible. Yeah? So what, how can we write it analytically? Analytically we will say that w minus z0 is the vector z minus z0 multiplied by similarity ratio k z minus z0. That's formula number 2, and you don't need anything but this formula. And if, for instance, we consider, there are some problems in your textbook, if we consider problem 7 from your textbook, find the formula for transformation of the complex plane that carries the unit disk about the origin to the disk with the center at point 5 of radius 3. So, problem 7 from your textbook. Find a transformation that carries the unit circle. Unit circle can be described z such that modulus of z is equal to 1. That's what I think they want. Modulus of this, or they want the disk, yes? It carries the disk. This is the disk bounded by the unit circle about the origin. Into the disk points z such that z minus 5 modulus is less than 3. So what shall we do? There was a disk about the origin of radius 1. Suppose this is 1, this is the origin. You don't even have to draw this picture, I just draw it for illustration. And you have to make out of this disk another disk with 1, 2, 3, 4, 5, right? Of radius 3, 1, 2, 3. So it will be huge disk. Don't even have enough room to show the whole disk, but the radius of this disk, this distance, will be 3. Texas goes forever. This is 0.5. So I will say, all right, we will just, you can do it in 2 steps. Perform a translation, then a homotety, or we can form a homotety and then translation. So first way we can do it, we can make T1 Z moves into Z plus 5, right? This way the origin will jump into point 5, and every point of the plane will move 5 units to the right. And then, and I will denote this. I will denote this new variable, let's say psi. That's a good name for it. Intermediate variable. And what T2 does, as a result of T1, I will draw a picture. As a result of T1, we had this little circle with the center at the origin. We will have this little circle moved, so its center will be at point 5 on the real axis. I hope this circle is not the same. Right? And then transformation T2. Transformation T2 do the following. It stretches from point 5, so this point will come here. Right? I will write it like this. W minus 5 equals 3 multiplied by psi minus 5. So from here I can find W equals 5 plus 3 psi minus 5 equals, now instead of psi I will substitute z plus 5. 5 plus 3 z plus 5 minus 5, and it will be 5 plus 3z. That's our formula for the transformation. And can we do it differently? Yes, we could do it differently. We could first make this circle into a big circle of radius 3. So T, I will write final, T equals T2 transformation composed with T1 of Z, T applied to Z, T2, T1 applied. This is sign for composition. Usually we'll just write T2, T1. And it will be 5 plus 3Z. Alright, what else could we do? Second method. It was the first method, right? The second method. We could make the following. We could perform a transformation, I call it tau 1, not to confuse, that moves Z into 3Z, so homothety goes first. This way, instead of this small circle of radius 1, we will first obtain a big circle of radius 3. So this is 1, this is origin, this is 3. And then, in the next operation, we will move this circle 5 units to the right. Translation. So my second transformation, tau 2, I will denote this variable, let's say eta, will change eta to eta plus 5, which we will denote W. So the result, W equals eta plus 5 equals 3Z plus 5. Z plus 5. For instance, what will be the image of point 1 under this transformation? If I substitute 1 into this formula, I will have W equals 3 times 1 plus 5, 8. 2, 8. Yeah, it looks like it will be the right point. So that's how we can compose transformations, and these are easiest examples. And I will remind you again that all these transformations, if you already have met them in elementary geometry, they preserve angles, so they have the property of conformality. Now we will learn something new, a little bit more unusual but very important for us transformation. It will allow us to create new geometries. That was important for us. And this kind of transformation is called the inversion. Inversion. And this transformation is kind of like this. W equals 1 over Z. That's the transformation. So So what happens with the number z? If I suggest, for instance, that z equals r e to the power I theta, then as a result of inversion, suppose z is somewhere here, z w will be 1 over r e to the power I theta, or I can write like this, 1 over r multiplied by e to the power negative I theta. So modulus of w will be 1 over r, and argument of w will be negative argument of z. So if z is this number, this is angle theta, so w will be on the ray going, making the angle negative theta with the real axis instead of theta, and the distance, I wrote it wrong, yes? The distance will be 1 over r. So for instance, if, let me make a bigger picture, it will be more convenient. If this is number z, this is angle theta, this is angle negative theta, right? W must lie on the same ray. I will suggest, just for this picture, that z is greater than 1, that modulus z is greater than 1, then modulus w will be less than 1. So it will be, for instance, shorter, it will be somewhere here. This is w, right? And the unit circle, those numbers that lie in the unit circle, their modulus will be the same under the inversion. Yes? So this is the unit circle, this is the unit circle. If z lies outside the unit circle, then w will be inside the unit circle, and vice versa. So if your point is located originally outside the unit circle, it will be inside. If it was inside, it will be outside. So I will draw the unit circle first. It will be more convenient this way. This is the unit circle of radius 1. And if some point, for instance, is here, z, as a result of inversion, it will be where? Just be careful when drawing these pictures. Try to be as precise as possible. Angle, this angle theta, so it must be angle negative theta. Suppose this is angle negative theta, and it will be outside the unit circle. W equals 1 over z. There is historically international, well-known international joke about the topic how to catch a lion in a desert. Suppose you are in a desert and there are various methods offered by various kinds of scientists how to catch a lion. You don't have weapons or anything. So it's very easy. So you are in a desert, suppose this plane is a desert and the lion is in the desert, yes? That's a lion. How will you catch it? How will you catch it? And the answer is very simple. The answer is very simple. You stay inside a unit circle, which is made into a cage. It's a cage in the shape of the unit circle. And then you perform an inversion. And as a result of inversion, the line will get inside of the cage and you will get outside of the cage. And so line will be caught. That's how mathematicians solve practical problems. So let's continue in the next lecture with the properties of inversions.